Question 4. Okay, so we're going to be looking at 3.7, question 4. And these are variations. So what we have to remember is when it's direct, we multiply. When it's inverse, we divide. And joint just means we have several different factors going together. So let's look at 4. So question 4 says the weight of a body above the surface of the earth is inversely proportional to the square of its distance from the center of the earth. What is the effect on the weight when the distance is multiplied by a factor of 2? So let's try to first figure out our setup. What does our setup look like? Okay, so the weight of a body above the earth's surface is inversely proportional to the square of the distance. So how would this look when we set it up? Well, the weight, the person's weight, the closer you are to the earth, the more you weigh because of gravitational pull, is inversely proportional to the square of the distance. Now, this one doesn't give you any numbers, okay, but it wants to know what happens when the distance is multiplied by a factor of 2. Okay, well, let's see what would happen if we do that. So let's let our distance be 1. So if the distance is 1, what is my weight going to look like? Well, that's going to be k over 1 squared, which is just simply k. Now, we're going to compare that when we change it. So if I let my distance be 1, my weight is just going to be a constant, right? Now, what happens if I double the distance? If I double the distance, that means I'm going to let my distance be now 2. That's going to double it, right? Because when you double 1, you get 2. Let your distance be 2. Now, if I plug in 2, what's going to happen to my weight here? All right, if I plug in 2, then that's 2 squared below, which is then k over what? K over 4. Now, look at how these compare. When I have a 4, when I double it, what happens? It doesn't decrease by a factor of 2. It decreases by a factor of what? 4. Why? Because your distance is what? In your original formula, your distance is squared. So I plugged in numbers so you would kind of see what happens. It's a fourth as much. Because if I use 1 just as a starting point, and I plug that in, I get my weight to be some constant k. Now, if I double my distance, so if I double the 1, when I double that, that's going to make it what? 2. Okay, and if I plug my 2 in, well, what happens when you square the 2? Makes it 4, right? So now instead of k, it's k over what? 4. So what happened to your weight? Your weight is a fourth as much. Because it changed by a factor of 1 over 4. So the weight is going to be 1/4 as much. So the further you are away from the earth, the center, the less you'll weigh. And that's on the distance squared, because it's inversely proportional. So your weight would be 1/4 as much. So that's what's going to happen to it, because you doubled the distance. And that's what they wanted you to see. Just plug in it in 2 values and see what happens. You could have used any 2. It would have gave you the same result. But I just chose 1 to start with, doubled it, got 2, and it's not going to be 2 down below, it's going to be 2 squared, which is 4. Question 8 is next here. Question 8 is joint variation. Now, what does it mean when we have joint variation? Joint variation means that you have several factors going together to give you a result. So we're looking at question 8 here, and we're talking about a car skidding on a curve. So the force needed to keep a car from skidding on the curve varies jointly as the weight of the car and the square of the car's speed, and inversely as the radius of the curve. So we've got lots of things happening here. We've got the force that is needed to keep the car from skidding out of control. So that's going to be our force. And how does the force relate to everything else? Well, if we read it, it says the force needed to keep a car from skidding on the curve varies jointly as the weight of the car and the square of the speed. So K is going to be our constant. We've got our weight and we've got our speed of the car, but the speed of the car is going to be squared, and it's inversely to the radius of the curve. So that is what your equation looks like. So again, how did I come up with these pieces? Let's read it and see. So the force needed, that's what we're going to start with. So we're trying to keep a car from skidding off of a road. So the force needed to keep that car from skidding off the road varies jointly as the weight of the car and the square of the car's speed, and inversely as the distance of the curve. So that's going to be down below for the inversely there. Weight is up top along with the square of the car's speed. Now we can plug our pieces in, right? And we should be able to find our constant K, and then we can finish the question.
Are you having it with the K too?
Well, what we do is the K is a constant. Okay, so K depends upon the situation. Now, K can be a variety of things depending upon the problem, like gravity. Okay, the effects of gravity is a constant.
Yeah, I was just included in the dividing. Or is it just weight speed squared?
Yeah, it's just going to be the weight times the speed squared divided by the radius, and we have to find the value of that.
Okay.
So K is going to be a number, like gravity. Okay, and we have to find it. Now, K can change because it might be one day it's different from another, because that K would be different if you're on a road when the pavement is dry versus when it's really wet, or maybe it's icy out. That would make the K change. So we have to find the K based upon those conditions and then evaluate it down with a new force. So you'll kind of see how it's done in just a moment. So we've got our formula set up, and we need to find our K. So what do we know? If the force of 3,000 pounds, or sorry, of 3,600 pounds, so the force in this case is going to be 3,600. That's the force needed to keep an 1,800 pound car. So that's your weight. Traveling at 20 miles per hour, that's your speed. From skidding on a curve with a radius of 600 feet. Okay, so these are the components that we need to keep this car from spinning out on a curve. We need to find K. Again, K can be different depending upon the road conditions. So these are the values that they give you. We need to find our K. So we're going to plug our numbers in. So we've got a force of 3,600. That's going to equal K times the weight of the car, which is 1,800 pounds, times the speed squared, so that's 20 squared. Divide that by the radius, which is 600. Now we're going to work this out. So let's go ahead and break up the numerator. Numerator, we've got 20 squared, which is going to be 400. We're going to multiply that by the 1,800. And that gives you this. That gives you 720,000 K over the 600. and that equals 3,600. And now we can cross multiply and finish, right? So that it all broke down. You can reduce it too. I'm just going to go ahead and cross multiply. So 3,600 times that 600. That gives me then this, which is 2160,000, and that equals your 720,000 K there. And now we can divide, and we'll reduce this down. And that is going to give us our value of K. And in this case, K comes out to be the whole number 3. So for that particular day, K is going to be 3. And again, that can change based upon road conditions. Or the road itself, depending upon everything, all those different factors. Each one goes in to give you that K. Now let's rewrite our formula, and then we can finish this question by finding the new force. So let's rewrite it. So now we've got our force is going to equal 3, because that's our K, times the weight times the speed squared over the radius. Now we want to change things. So what are we going to now try to do? Okay. We want to know the force, so we want to find the force. It is going to be required to keep the same car from skidding on a curve with a radius of 640. Speed of 50 miles an hour. And let's see. Same car, so that weight is still going to stay the same. That weight is still going to be that 1,800 because it's the same car. They don't give you the weight, but they say it's the same because it's the same car. So now we're going to plug it in, and we're going to see how much extra force is going to be needed to apply. So 3 times your 1,800 here, times the 50 squared over 640. So what's my new force going to be needed? We've got 3 times the 1,800 times that 50 squared. Divide that by 640, and that gives you this. That gives you now 21,000, if we round, 94 pounds. So why did it increase so much? What was the big difference here? Because the other one was only 3,600, right? It only took 3,600 to stop this car before. But what changed? Okay. Well, what changed and what made the big difference now is what? Is that speed. When you square it, see, it way more than doubled it. Right? It made a big difference because of the square of that speed. The speed is what did it. Okay? Is everyone all right with that so far? So that would be your answer there. And I just rounded to the nearest. It says 100th of a pound. I rounded to the nearest pound. That's close enough. All right. Let's see. Round your answer to the nearest pound of force. Yep. So we rounded it correctly. So it's going to be about 21,000 pounds to stop that car. And again, why is it so much more than the 3,600? Because the speed is squared. And if you think about things, you know anything about driving a car, when you increase the speed, it takes a lot more force to try to keep that car on the road when you go around a curve. The speed is the number one thing that really makes the car want to spin out. Did we have any others out of 3.7 to look at? Any others? Okay, well, then we'll go ahead and begin now looking at 4.1. And 4.1 is inverses. And we're going to be talking about what inverses are, and then we're going to be finding them as well. So when we talk about inverses, we have the horizontal line test. Now remember back in chapter 2, when we talked about graphing and we talked about functions, right? We had the vertical line test. And we drew those vertical lines, and if any vertical line touched the graph at more than one place, right, then it was not a function. Well, we also have what's called the horizontal line test. And the horizontal line test says this. You draw horizontal lines. If any line touches the graph at more than one place, it is not one-to-one and has no inverse. So when we did the vertical one, right, we talked about functions, and you drew those vertical lines, and that told you if it was a function or not. Now we're going to be talking about horizontal line tests, and they tell you if it has an inverse. Now the inverse is just the opposite. Now not all functions have inverses. Some do, some do not. Okay, but think of the inverses like its opposite. Now when we look at these graphs, we're going to be looking and we're going to be drawing horizontal lines. And so some functions have inverses, some functions do not. When it says one-to-one, okay, these words are used interchangeably. One-to-one means it has an inverse. So if it's not one-to-one, it also has no inverse. Now, these graphs, we're going to see if they have an inverse or not. See if they're one-to-one and have an inverse. So do the graphs have an inverse? And one-to-one. So I'm going to draw you some pictures here. We'll probably do 3 of these. And we're going to see if they have an inverse and if they're one-to-one. Now, one-to-one just means it has an inverse. They're the same. Those words are used interchangeably. Okay, so some of these are going to have inverses and some of them are not. Now, the first one, does it have an inverse? Does this one have an inverse? Yes or no? No. Sorry, it does, right? Why would this one have an inverse? If I draw my horizontal lines, does any horizontal line touch that graph at more than one place? No. That means it has an inverse and it's one-to-one. So that one has an inverse and it's one-to-one. Now what about the squaring function? Does it have an inverse? No. Why not? Because see, it touches twice. So this one has no inverse. And is not one-to-one. And what about this one down here? Does this one have an inverse? It does, doesn't it? Right? Because if I draw horizontal lines, does any horizontal line touch the graph at more than one place? No. Okay, so this one would have an inverse. So this one down here has an inverse, and it is one-to-one. So we use the horizontal line test to see if a function has an inverse or not. What does it mean if something has an inverse? Well, if a function has an inverse, it's going to be reflectable around that line y equals x. So I'll give you some examples of inverses here, and we'll talk about why these are inverses of each other. So I've got two different colors that I'm going to use to do two different graphs, and we're going to talk about these, and we're going to see why these are inverses. So we have two graphs here, and these are inverses. So this one would be f of x, okay, and this one would be f inverse of x. Now these are inverses of each other because if I draw that line y equals x, I should be able to fold one graph over and get the other, right? If I fold this piece over, this dotted line here, what does it fold over and give you? It gives you the other one, right? So this one is your f, this is your inverse. They should be able to fold it over around that line y equals x, okay? And that's going to make them inverses of each other. Let's look at another one. So these are inverses. Here's another one that's an inverse. These are also inverses. Now, why would these be inverses? Well, if I draw my line down the middle here, if I draw that dotted line y equals x, what happens? If I fold this piece over across that dotted line, what does it do? Matches up with that one, right? So they have to be able to be folded over. This piece here matches up with that piece there. For them to be inverses of each other, they have to be able to be folded over that line y equals x. So those are inverses. These are also inverses because you can fold them over. So these are what are called inverses. And that also goes back to the fact that you can compose them together and get out an x. If you can compose two functions together and get out an x, then they are inverses of each other. Here's two functions that would not be inverses. And let's see why these are not going to be inverses. So here's two new functions. And why would these not be inverses? Okay, well, these are not going to be inverses because if I drew my dotted line here, and this is always the same, y equals x, if I'm here, does it match up with this over there? No, because see, it would match up over here. Right? This one, when I fold it across the dotted line, when I fold it over, it makes it here. It doesn't map to the green one. So these are not inverses of each other. Because for them to be inverses, you have to be able to fold across that line y equals x. Now what we're going to do, and this is what the most of this section is going to be finding the inverses. So we're going to be looking at these algebraically, and we're going to be finding the inverses. And here's how you do it. So to find an inverse, first thing you do is you check to see if the inverse exists. Now, most functions have an inverse, but one particular one that we work with a lot that does not have an inverse is a square. So the squaring function, x squared, has no inverse. Most other functions do. Now, it could be that you have a restricted domain, and then it would have an inverse. But most of the time, if you just have a squaring function, it's not going to have an inverse, unless it's got a specific domain with it. Once you've determined if it has an inverse, then what you do is you replace f of x with y. And then after you've replaced the f of x with the y, then you interchange or swap x and y. And then your last step, what you do for the last step is you solve for y and replace y with f inverse of x. So this is our step-by-step procedure for finding an inverse. Now, most functions, again, have an inverse. There are a few that do not, but most functions are going to have an inverse. So we're going to do a lot of these, and they're actually fairly simple. The only ones that pretty much don't have an inverse are x squared. But if they restrict the domain, then it does have an inverse. So let's start off with a really simple one. And let's start with this one. We're going to find the inverse here. This one will be a line. About f of x equals 3x minus 2. All right, and I want to find the inverse. So this is a line. And lines have an inverse. The only ones that do not, that we work with, are x squared. X squared does not usually have an inverse, again, unless the domain is restricted. So what do? We determined that it has an inverse. Then we replace f of x with y. So we did that, and now we switch or interchange out the x and the y. So now it becomes x equals 3y minus 2. So you switch or you interchange the x and the y. And now to find our inverse, what we do is we solve it for y. So we're going to go ahead now and quickly solve this for y. So I'm going to add my 2 to each side. So 3y equals x plus 2. We'll divide by our 3. And now we've got y equals 1/3 x plus 2/3. Once you have that, that is now your inverse. So your inverse is f inverse of x, and that's 1/3 x plus 2/3. Now, I'm going to graph these and I'm going to show you why these are inverses. Because if they are inverses, they should be able to be reflected around that line y equals x. So let's take a moment to graph these. This is the only one I'm going to graph, but I want to graph this so you see how these are inverses. So how would I graph this one, the very first, f of x? Well, that's pretty simple because that's a line. So where would I start at for this one? If I was going to graph this. It's a line, so I have a minus 2 on the end, so that means I've got to do what? Start down 2 units. So I'm going to start right here at 0, -2. And what's the slope on this one? Yep, 3. So that means I'm going to go up 3 and over 1. So 1, 2, 3, and over 1. We'll draw our line. And what about the other one? Because this is your f of x here. What about its inverse? What would its inverse look like? Well, its inverse is here at 2/3, so that's about 1. So we'll start right about there. And then what am I going to do? I'm going to go down 1 and over 1, 2, 3, because this is a line. I'm going to graph them like that. Now, if I draw my line through, and I know my graph is probably off a bit, but if you draw your line y equals x, then they should match up. I should be able to fold this one over. So I should be able to fold this x here, folded over the dotted line, and it should match up with the blue one below. Okay, and same thing over here. This one should match up with that one. So it should be able to fold them across the dotted line, y equals x, and they should match up. I'm not going to make you graph these. I just want you to see what inverses are. So inverses, they fold across that line, y equals x. Okay, now let's do some more of these. So we're going to go ahead and find the inverse again of a new function. And how about we look at a rational one? How about f of x equals 4 over x plus 1? So the first thing that we need to do is we need to figure out if it has an inverse. Does it have any squares in it at all? No. So it's going to have an inverse. Right? The only ones that don't, generally speaking, are the squares. Now, what do? Our procedure is we replace f of x with y. And then once we have that, then what do? We interchange or swap out your x and your y. So, replace f of x with y, interchange or swap out your x and your y, and now we need to go ahead and solve this for y. So the first thing that we're going to do is we're going to cross multiply here. So when we cross multiply, we get x times y plus 1 equals 4. So cross multiply. Now I do have to get rid of my parentheses, so I'm going to have to distribute that x through. And so that's going to be xy plus x equals 4. And again, we're going to be solving this for y. So I distributed that x through. We're going to go ahead and solve this for y. So what do I need to do? I'm going to move that x over. So xy equals a minus x plus 4. And what's my last step going to be to solve it for y? Can someone tell me? I need to get the y by itself, so what do I need to do? I need to divide by what? X. Okay, so let's do that. And what does my inverse look like? Okay, well, that gives you y equals now, when we divide through, a minus x plus 4 over x, and we replace y with f inverse of x, and that's going to be your answer. So your f inverse of x is minus x plus 4 over x. So what did we do? We first figured out if it had an inverse, and then once we figured out it had an inverse, we found that inverse. So let's try another one here. What about we have f of x equals, how about 4x cubed minus 7? Okay, so we want to find the inverse here. So what do we do first? Does it have an inverse? Yes. What does not have an inverse? A square. Now, the square won't have an inverse unless they restrict the domain. So this one has an inverse. What do we now do? We replace f of x with y. And then we swap, or we interchange the x and the y. Right? So we replace f of x with y, and then we switch x and y out. And now what do we need to do? Now we solve it for y. So we're going to add 7. So 4y cubed equals x plus 7. We'll divide by our 4. And now we've got y cubed equals x plus 7 over 4. And how do we get rid of this? How do we finish this out? Well, how do we get rid of a cube, do you think? Okay, what's the opposite of a cube? How do we get rid of a square? We take the square what? Root. So how do you think we're going to get rid of the cube here? Take the what? Cube root. So take the cube root of both sides. And now you've got your inverse. So your new inverse is f inverse of x. And that's going to be the cube root of x plus 7 over 4. Okay. Now let's try another one. Okay, so f of x equals x squared minus 8. Now, what's the matter with this one? Is this one going to have an inverse? No. This one has no inverse. And not 1-to-1. So there's nothing that we could really do. Because it has no inverse. Why does it have no inverse? All right, it has no inverse because of the x squared there. So that one has no inverse because of the x squared. Now, if the domain was restricted, you would have a possibility of it having an inverse. But this one does not have an inverse. Why not? Because of the x squared there. This one, though, has an inverse. Now, why would this one have an inverse and the other one did not? Okay, this one has an inverse because it restricts the domain. And this one says your domain has to be greater than 0. So what that is that's half of the graph. Okay, because if I look at this graph here and I were to graph this, we've graphed a lot of these. Okay, if I were to graph this one, this is 2x squared plus 5, so I would start up 5 units. And if I were to just graph it, then I would get this. Right? I would get a u. That does not have an inverse, does it? But what about your domain here? What does the domain say? X is greater than or equal to 0. So that means, this is your x here, that means you're not even including half of the picture. So when they restrict the domain, that means you only have half of it and the inverse actually exists. So if it's an x squared, but they give you a restriction, then it has an inverse. If there's no restriction, like this one, right? This one has no restriction, so if you were to graph it, this one would be down 8 and look like this. And see, this one has no inverse because, look, this one would fail the vertical line test, right? But if you restrict the domain and you restrict out and say x is greater than 0, then that means that half doesn't exist. And if you just have half of the graph, then it can have an inverse. So this one does have an inverse. So let's go ahead and find that inverse. Okay. Now, what are we going to do? We replace f of x with what? Y. Then we interchange the x and the y. And now we can go ahead and solve this. And we get 2y squared equals x minus 5. Okay, we'll divide by our 2 everywhere. Now we've got y squared equals x minus 5 over 2. How do we get rid of a square? To get rid of a square, we take a square what? Root. Now, we don't have to worry about the plus or minus because of that, right? Normally, you would have a plus or minus, and that's why it would have no inverse. But because of the fact that we know it's only half of the picture, because this is greater than 0, we don't have to worry about the plus or minus, so we don't have to deal with that. So now we just get our answer, which is going to be y equals the square root of x minus 5 over 2. And that means that f inverse of x is the square root of x minus 5 over 2. Now, what we need to also do is we need to find our domain of the f inverse. To get that, we have to find the range of the original. So if I look at this, if I plug in 0, what do I get out for my function here? If I plug in 0, I get out what? Okay. 2 times 0 squared is still 0. Plus 5 makes it what? 5, right? Now, look at your graph. Here's your graph here. We want to find the range. Does this graph ever go below the 5? No. So your range is going to be y is greater than or equal to 5, and that, when you switch them around, becomes your domain down here. So now x has to be greater than or equal to 5. So when you have a restriction, you have to be careful, and your domain and your range switch around. So you have to find, you're given the domain, you have to find the range. Your range now becomes, range is the y part, range now becomes the domain. And you can't have x bigger than 5 because that would make this non-existent. Let's look at another one. Let's try another one here. And this one's going to be similar to your homework. I'm just going to change the numbers a bit. So this is very, very similar to one of your homework questions. Looks like question number 6. Now, first off, does it have an inverse? Yes. Even though it's squared, we restricted the domain. So we restricted the domain to be x is greater than or equal to 6. That way it works. If it fell below, you would end up with imaginary numbers. So we restricted the domain. Now, what do we need to now do? We need to replace f of x with y. And then we interchange or swap out your x and your y. So swap out or interchange your x and your y. And now we can solve it. So how do we get rid of a square root? We get rid of a square root by doing what? Squaring. So we're going to square both sides. Okay. And that gives you now y squared minus 36 equals, when I move it over, the x squared. So we're going to have to add that 36 over. And now we've got, I move it up so we can see what we've got here. Now move that over. Now we've got y squared equals x squared plus 36. And how do we get rid of a square root again? Or sorry, a square. Well, if we have a square, we get rid of a square by using the what? Square root. Now, we don't have to worry about the plus or minus because we restricted the domain. So we had to restrict that domain. Okay, and now when I do that, I get y is going to equal the square root of x squared plus 36. So my f inverse of x is the square root of x squared plus 36. I still need to, though, go back to finish this one out and find my domain. Okay, so let's go back and look at the original. Now, here's the original, and your restriction was x is greater than or equal to the 6 here. What happens if I plug in the 6? Okay, if I plug in the 6, well, 6 squared is what? 36 minus 36, that makes that now what? 0. Okay. If I do a 7, it would be larger, right? So what's my range going to be? Y can never be below 0 because the smallest it can ever be is going to be 0. If I plug the 6 in there, right, that gives you 0. I can't plug in any negative numbers, and if I plugged in 9, see, that would then be 81 minus 36, which would be positive. So your range, your y, has got to be greater than or equal to 0. And if that is your range, then it comes down as your domain. And so x is now, for your domain down on your inverse, greater than or equal to 0. Let's do one or two more of these. And then that'll finish up today's lecture. So let's say I gave you this. Okay, you want to find the inverse of this. This is another line. It's just written a little bit differently, but it's another line. Now, this one has an inverse, right? How do I know it has an inverse? Does it have an x squared on it? Nope, so we're good. X squared can have an inverse if they restrict the domain. Most of these are going to have inverses, but x squared does not unless they restrict the domain. So this one's going to have an inverse. So we're going to go ahead and replace f of x with y. And now we switch out or swap out x and y. And we want to solve this. So, if I want to solve this, what do I need to do? So I want to solve this for y. So I'm going to clear out my fractions. So multiply everything by the 5 here. That's going to clear out my fractions because we're solving it for y. So distribute that 5 through, and that is now 5x equals, now the 5's cancel, 4y, 5 times a negative 3, that's a minus 15. We can solve this easily for y, so we're going to add our 15 over. And that leaves me with 4y equals now 5x plus 15. Divide by our 4, and now we're done. So we divide it all by that, 4. And that leaves me then with 5/4 x. You can write as one fraction or two, it doesn't matter. So 5x, right, plus 15 over 4. You can break it up, doesn't matter. And that is your F inverse. So we found our F inverse, which is 5x plus 15 over 4. And you can split that up into two separate pieces if you want. But that is your inverse. Let's do one more, and this will be it. So let me find the sign-in sheet. And then I've got quite a bit of old homework to pass out to you. I've got everything graded. I always try to grade things as soon as you turn it in. So the next class period, I always turn things right back to you. Let me find the sign-in sheet here. I just had it a moment ago. There's the sign-in sheet. There's the sign-in sheet. Okay, so let's do one more of these, and then please make sure you pick up your homework today. I've got quite a bit of graded homework. It's been piled up for a while. You may not have picked it up in a while. A lot of you turned in a lot of homework on Tuesday, and I got all that graded. So quite a few of you have homework to be picked up today. So before you leave, please make sure you pick up that homework. But let's do one more. So let's work with this one. We're going to find the inverse here. So what's the first thing I need to do? Does it have an inverse? Yes. How do I know? Does it have any squares? Nope. So it has an inverse. Okay. Cube roots have an inverse. So I replace f of x with y. Now what do? Now we swap out, or we interchange the x and the y. So those got swapped out, right? Just switch them around. Solve it for y. So I'm going to add that 3 over. Bless you. So that is now x plus 3 equals the cube root of y plus 7. Now, I want to solve it for y. So how do I get rid of a cube root? What would you do to get rid of the cube root here? You get rid of the cube root by doing what? Yep, someone said it, cubing, right? So we're going to cube both sides to get rid of that. And that leaves you now with x plus 3 quantity cubed equals y plus 7. And what's my last step going to be here? Move that 7 over. And we now have y equals x plus 3 quantity cubed minus 7. And so f inverse of x, which is our functional inverse, is x plus 3 quantity cubed minus 7. Okay. So there is your inverse. Now again, a lot of you have turned in homework. and haven't picked it up in a while. So there's quite a bit of assignments to be picked up. So I'm going to go ahead and put these out for you to pick up. And once you sign the sign-in sheet, you're free to go for the day. Remember, if you're short any assignments, look in your Canvas gradebook. If you're short assignments, you can find them, print them off, and hand them in. But here's your homework. So please stop by and pick up your graded homework before you